All right, guys, welcome to this video. I'll be doing the first six problems of the USNCO 2025 local exam. This is going to be about stoichiometry. So let's get started. All right, number one asks us for how many nitrogen atoms are present in 486 grams of dinitrogen pentoxide. So what we first do is find out the molar mass of dinitrogen pentoxide. So we're going to do 2 times 14.01 because that's the molar mass of nitrogen times 5 times 16 plus 5 times 16. So that's the molar mass of oxygen. That's 108.02 grams per mole. So then we can do 486 divided by 108.02, which is equal to about 4.5 moles of nitrogen pentoxide. But we need to multiply this by 2 to get the nitrogen. So basically, I don't know why it's negative now. Oh, like that's funny. So it's gonna be 9 moles of nitrogen, right? So let me do this on my calculator. 486 divided by 180, 108.02 times 2 times 6.022 times 10 to the 23rd. So that's 9 times 6.022 times 10 to the 23rd. This is Avogadro's number, which is the amount of atoms in a mole. So we get 5.42 times 10 to the 24th atoms. Now you want to make sure that you don't make the mistake of thinking that it's just the amount of moles in this. So remember when I was first doing this, I made that mistake. But remember, the subscripts are the amount of moles of the individual atoms, elements. Okay, what is the empirical formula of a compound that is 50% sulfur and 50% oxygen by mass? So you actually don't need to do the math unless you really want to check your answer. But what I'd like to do is if you look on the periodic table, it's a shortcut. Oxygen is right above sulfur. So sulfur is right below oxygen. And that's because they're in the same group, so they have similar properties. The molar mass of oxygen is 16. The molar mass of sulfur is 32.066. So that means if we have 50% sulfur by mass and 50% oxygen by mass, to get to the same number or the equal masses, there has to be 2 moles of oxygen for every 1 mole of sulfur. So it's gonna be SO2. All right, next, how much chlorine is required to completely consume 13.5 grams of aluminum to form aluminum chloride? So let's write the balance equation here. So we have Al plus Cl2 gives us AlCl3 because aluminum has a +3 charge. So we're going to put 2 right here, a 3 right here, and then a 2 right here. Yeah, that looks right. Okay, cool. So aluminum's molar mass is 27. It's about 27. So what we can do is 13.5 grams of aluminum times 27, or it's at the bottom, but 27.0 grams of aluminum per 1 mole of aluminum, which means we have about 0.5 moles of aluminum. And then we can do stoichiometry, 0.5 moles of aluminum. The stoichiometry ratio is 2 moles of aluminum for every 3 moles of CO2, chlorine gas. Cool. So this is going to be, remember, it's like 1.5 divided by 2, so it's 0.75 moles of CO2. And then CO2, chlorine is 35.45 grams per mole, but because we have 2 of it here, it's actually 70.9. That's a good thing to keep in mind. Oxygen gas isn't 16, it's 32 actually because there's 2. And oftentimes they don't really have to mention that it's a gas or diatomic. Okay, so 75% or 0.75 times 70.9 is equal to 53.2. This is kind of big, but so I'll erase it so we have space for the next one. So this question is a fun one because it's asking about the concentration of iodide. We have two iodine salts here. Okay, so what we want to do here is we did first find moles of salt, then find moles of iodine ion, and then we have to find the concentration because it's not just done there. It's not just that. So that those are the rules there for our goals. Okay, so remember that the number of moles is equal to MV, molarity times volume. So if we go here and we start with 0.5 liters of 0.15 molar potassium iodide. So 0.5 times 0.150. This is 0.075 moles of potassium iodide, which is because it dissociates into a 1-to-1 ratio, right? K plus and I minus, one of each. It's also going to be 0.075 moles of iodine ion. And remember, 0.5 liters. That'll come in handy later. Okay. Next, we have 0.250 liters of 0.200 molar calcium iodide. And this one's important to know that we have two iodines in here. So we'll have to double the moles of the salt to get what we actually need. Okay, so 0.250 times 0.200. So maybe, okay, that's not what we wanted. I'll put in my calculator. This is 0.050 moles of calcium iodide, which will multiply. Remember, this is what it actually is. So we'll multiply by 2 to get 0.100 moles of iodine ion. We'll add these together. So in total, we have 0.175 moles of iodine, and then we'll divide it by the sum of the liters, the sum of the volumes. So 0.5 plus 0.25 is 0.75 liters, which is or 0.50. Remember your sig figs. This is 0.23 repeating. So this is the answer, C. All right, next, the only source of malachite, or it's the only source of copper in an ore is the mineral malachite. 1 kilogram sample, this ore is smelted to obtain 47 grams of metallic copper. Assuming a complete recovery of the copper, what percentage by mass of the ore is malachite? So let's find first the moles of copper we have. So 47.0 grams copper divided by 63.546 copper, or grams, I guess. This will give us our moles to 0.74. Okay, so we see copper is, there's two coppers in this ore. So you have to multiply this by 2, which will give us 0, or not 0, 1 point, or my bad, actually, because we need to divide this by 2, because that's the stoichiometric ratio. So again, guys, don't forget your stoichiometry, right? It's like this, 0.74 moles of Cu times 2 moles Cu for every 1 mole of malachite. So this is actually going to be 0.37, if I'm not mistaken. Yeah, moles of malachite. And then we can multiply this by the molar mass, 221.1, which is 81.807 grams. And then if we divide this by 1,000 grams, because this is a 1 kilogram sample, this is going to be 8, oh, that's really bad, 8.18%. So B is our answer here. Okay, this last question is a really fun one because it's not just stoichiometry here. It's actually boiling point elevation. So the equation for this is the change in boiling point is going to be equal to the Van 't Hoff factor times the boiling constant. It's a really weird name. Don't remember it. Times the molality. But okay, so what do each of these mean? So the Van 't Hoff factor is just how many particles are formed or how many particles are released after dissociation. So for sulfuric acid, it's 3 because we have 2 hydrogens, then 1 sulfate. 3 here because we have 2 sodiums, and then we have 1 sulfate. 3 here because we have 2 lithiums and 1 sulfate, but only, oh, 3. Yeah. And then 2 here because we only have 1 magnesium and 1 sulfate. Okay, so the KB for water, it's 0.512. I don't remember the units, but it's okay. And then the molality is just uh molality is moles over mass, kilograms. So for this one, it's going to be 0.1 kilograms because we only have 100 grams of water. So we're trying to find the biggest increase in this, right? Now, if 0.512 is always going to be the same between all of these guys, you can already cross out magnesium because it only has 2. These these threes will be a bigger factor in determining the boiling point elevation. So now we just have to find, because look, I is going to be the same. They're all going to be 3s, right? We just have to find which of these will give the biggest molality. That's going to be the one with the smallest molar mass, so that 10 grams are going to be a lot. So it's going to be hydrogen here, because natrium or sodium, it's like 23. This is 1.008. Lithium, like 6.74. And sulfate is going to be the same throughout, right? So A is going to be your right answer. So you see, guys, for 6 and also for 2, you don't really have to do the math. You just see the patterns. And obviously, in the end, and with the harder questions, you're going to have to do the math, especially for the national exam. But if you can get away with these shortcuts, it's going to save you a lot of time.